Okay, so I'll talk logistics first real fast. So exam is Tuesday. It is regular class time, regular place. It is mostly, or I'd say two-thirds calculation, one-thirds concept, multiple choice type questions. If you look at the last year's exam, you'll see kind of the layout it'll tend to be in. You can bring a cheat sheet with whatever you want on it, as long as it's just the front of an 8.5 by 11 sheet of paper. It can be examples. It can be uh, something you find on the internet that's like a shortcut way to do something. It can be whatever you want. A equation sheet will also be provided, and it's got all the main equations that I think you would need in order to solve any problems. It's not about memorizing them, it's about being able to apply them. Um, I think that's the main logistical bits. So now I'm just going to go through each chapter and highlight what I think are the most important bits and try to avoid going on too many tangents so that you know the main things. But this doesn't guarantee this is it. I just want to say, like, I'm going to push to try and get a problem related to so and so on there. That doesn't mean I'm only going to have problems on so and so on there. So let me do that for each chapter. Um, all right. And like the early lectures, I have to hide the meeting control stuff, and that means I can't see chat usually because my tablet really does not like that. It waits out. So if anyone has a question in chat, someone please let me know. Okay. Unit conversion is not heavily stressed on exams, and in fact, I try to keep most everything in SI so you can avoid having to do any conversions because you've done enough of them for the homeworks. They are just a skill that I think by now is probably pretty set. Significant figures are not on there because we've never worried about those. Trigonometry is absolutely on there because that's the basis for any of the vector addition and other vector related stuff that we've done. But it is only going to be on there in that sense. There won't be a kind of generic trig problem. Similar for inverse trig, similar for calculus. So really chapter 2 is where the physics, the meat of this kind of starts. And it will be things like position time graphs. So can you, from a position time graph, tell me about the average velocity of something? Can you give me a sense of instantaneous velocity, speeding up, slowing down, that sort of thing? For, okay, still position time stuff. For instantaneous velocity, if you're given a function of time, position as a function of time, can you figure out the velocity from that? So can you take a derivative? Can you interpret when the velocity is going to be zero, meaning that things come to a stop? Can you figure out when it's going in the negative direction, the positive direction, and again, speeding up or slowing down, which requires you to think about the second derivative, the acceleration as well, or at least think of it in terms of these graphs and say, is the slope getting more and more negative while the velocity or the slope itself is negative? That would be speeding up in the negative direction, similar stuff like that. Acceleration time graphs also fall under the position time graph stuff. Knowing how to know if something's speeding up or slowing down. And then the big one, as far as calculation, is applying the kinematic equations. Since they get kind of rehashed in chapter 4 for projectile motion, it's likely that there won't be a lot of just horizontal motion related kinematic equations, maybe a few questions on those, and few, if any, on free fall explicitly. Instead, it will be on projectile motion because the vertical component of projectile motion is free fall. So questions like these of similar difficulty, maybe a slight bit harder, but definitely easier than homework problems tend to be, are what I am kind of expecting to have on the exam for kinematic equation stuff. What to remember from free fall is mainly this. So for conceptual questions, do you know that the acceleration is always that and never zero, no matter how much our brain wants it to be zero at certain points? Um, that the velocity is zero at the top if something's going straight up and down. If it is a projectile being launched at an angle, we can still say the vertical velocity is zero, but the horizontal is whatever it was when the object was first launched. So questions like these are still good to look at because they help you do the projectile motion version of these where the thing's also moving left or right while it's going up and down. Graphical integration may be one problem, and it's one like this, where it's you find the area of a triangle or something, not real integration, just these kind of cut and dried formulas for areas of rectangles, areas of triangles to find the change in velocity or change in position from a graph where acceleration or velocity is not constant. Chapter 3, vector addition is the main focus. So can you find the components of a set of vectors? Can you add those components to find the components of the overall or resultant vector? And can you, from that, write that vector in both component or rectangular form, or in the alternative magnitude, angle, or polar form? So component form is, I gotta come down here a little bit more. Uh, that right there, just find the x and y components of your resultant vector, and then it's ax I hat plus ay j hat. This is magnitude, angle, or polar form. And this example right here is a very good one to look at, as is the, I think we used the bird watcher example in the next chapter, also very good. So finding overall displacement is the physical example that you'd be, or physical type of problem you'd be solving. Um, in chapter 4, very similar things to chapter 2. It's just you have to do a lot of it twice. So if you're given the position as a function of time with both x and y components, can you find the velocity by taking a derivative? Can you find the acceleration in the same way? Can you do vector addition? This was the birdwatcher one I was talking about. It's another good example. Um, Still finding acceleration, taking derivatives, all that. But the big meat of this chapter was projectile motion. So the main properties of projectile motion that are most important not to forget, because they are not things that you're told, they're things that you need to remember are true. Vertical acceleration, still always 9.8 meters per second squared downward. Horizontal acceleration, there is none. That means that horizontal velocity does not change. It is always the same value. Vertical velocity works just like in free fall. Um, these problems on these two pages are good ones to be really familiar with. And I think of a comparable level to what could show up.
Professor, on our
Yes.
homework, there were a few problems that dealt with um, like someone jumping off of a flat surface. So the angle the angle that the horizontal was on was zero, and
Mhm.
then they would add like 3 feet to it. Could we expect one of those on the exam?
So it would be like you've got something either rolling or someone jumping horizontally off of something like that.
Yes, sir.
Yes, that is a possibility. Um, I kind of end up thinking of those as easier ones because you know that this is your vertical, or excuse me, your horizontal component, and so you've already figured it out if you're told that, and then only the vertical component has to be figured out. But um, maybe I could see conceptually they're a little bit weird because we're not always used to thinking of Vy as instantly zero from seeing a picture like this. Are
Well,
you, yeah,
the
go ahead.
the weirdness was not that they started us out with the vector component y, or the velocity in y and x, and then we had to back our way into time, and it was just funky. And I may have
Mm,
screwed up some manipulations within the the actual formulas. So it was just
Okay.
weird because it was that kind of flavor.
Okay. Um, it is a possibility, but usually when I have problems like these, they end up being a single problem gets broken up into maybe two problems or three so that you get the intermediate result you need for the next step. But I also try to, on that next part of the problem, say, all right, now assume the value is this. So it's not hinging on if you got the previous question right or not. Okay. Um, all right. That's big ideas. So if I had to put it in a nutshell, biggest things would be kinematic equations and vector addition. Concepts are free fall acceleration slash projectile motion accelerations and what acceleration and velocity mean, how they relate, and oh, position time graphs. That was the other kind of big thing that you can kind of see as a third thing in addition to kinematic equations and vector addition. Okay, so that's a very haphazard overview of what we've done so far. Now I want to dedicate the rest of the time to if there's any clarification needed or if there's questions on problems that we want to go over. So, questions.
Um, I actually have one. Vector addition is slightly blurry. Could you work a vector addition problem? It's
Yeah,
just the issue of whether you choose cos or sine.
yep, no problem. All right, let's come over to these and see if I can find one that has some meat to it so we can find multiple components. Uh, for what did I do there? Whoops, silly. Okay, find so 35 is an option. I think there was one that had even more vectors. Okay, I'll do both 35 and 36. How about that? So we have three vectors, A, B, and C. I'm going to, so sometimes it would be more kind of buried in a word problem, but it sounds like it's really just the component bit of this that's a little bit hairy. So we'll go fast so we can get to that part. A is 56 kilometers east. B is 11 kilometers, 22 degrees south of east. So that would be, you look east, turn south of that, 2 degrees. It's 11 kilometers. My vectors are definitely not to scale. And 88 kilometers, 44 degrees west of south. So that means I look down south and then I turn west from that. So south is this axis. So I'd be looking at, I don't know, make it a long vector, 88 kilometers. And even if my picture is not to scale as far as all the vectors, my drawing, the components of it may not be exactly what I get numbers wise, but it still gives me something to go off. So my resultant would be, oh, let me straighten that down. Resultant would be that vector right there, A plus B plus C. And so I need to find my X and Y components. So A, I don't think is the problem, so we'll just say real fast. AX positive 56 kilometers, AY is 0. But B and C, let's look at those in a little more detail. So I'll show you both ways you could draw the components of B and C and show you all the ways you could find these components. So B, you could think of that as you have to go to the right by some amount and down by some amount. That will get you from one end of B to the other. You could also think of it as going down by some amount and then to the right by some amount. whether I do one way or the other, one order or the other, the component lengths and their directions are the same, and that's all that matters. So if I am looking at this 22-degree angle, I want to find this would be my x component of, oops, x component of vector b. This would be my y component. So how I know instantly whether to use cosine or sine is my component touching my angle? Now, I might look at this one over here and not be sure because I don't see an angle. So the first thing you have to do is decide what angle it is you're referencing. And if the angle's not in your little triangle you're worried about, you have to find that angle. So over here, I would say, okay, I need to figure out what this angle is. It would be what, 68? Nope, 58? 68. It would be 68 degrees, complementary to 90. So I'll come back to that. For this 22-degree angle, though, I can see that BX is touching that angle. It is adjacent to it. It's something cosine. BY is going to be something sine because I have to go across from my 22-degree angle. I can't get to BY without crossing to the other side of the triangle. So I would use sine for that. If you want the kind of trig justification, it is that cosine is adjacent over hypotenuse, and if you rearrange, you'll end up with the adjacent side equals hypotenuse cosine 22, and similar for sine.
So
But
it's whichever sides that it's bx and by. So it would be cosine with the 22 because it's opposite over adjacent. By is opposite. Bx is adjacent.
yes, that's exactly
Okay.
it. Yep. And so I would know that since my hypotenuse, which is the magnitude of my overall blue vector B, is 11 kilometers, this component will be 11 cosine 22 in the positive x direction. By would be negative, because it's downward, negative 11. I'll drop units just to make it less messy. 11 sine 22. And I think what will really put the nail in this coffin is, say I did use that 68-degree angle, I can still find BX and BY, but this side is BY, this side is BX. So which one of those two is touching my 68-degree angle?
By.
BY. So I might look at that and be like, uh-oh, because now I should use cosine for BY. And then what about BX?
Sine.
Sine. Have I done something wrong here?
No, it's just the angle you're relative to.
Yeah. And if you put cosine of 22 degrees in a calculator, it is sine of 68 degrees. It's the same number. So these are equally valid ways of finding BX. For BY, it's equally valid to use sine of 22 or cosine of 68. It just is whichever one you chose to go with. And that's what I like about not sticking myself to BX is always cosine, BY is always sine, because that forces you to use specific angles. And if you don't, or you forget that you have to use specific angles for that to work, then it messes you up and you have no idea why. Does that make a little more sense?
Yes, sir. Now, if they were to give us the two components, they let's say they give us a vector b, they
Mhm,
give us that the by component, the bx component, and they want us to find the resultant. How do
mhm.
we go backwards?
Okay. So for that, the resultant I could think of in either the rectangular or polar form. So the rectangular is a little bit like, well, duh. So I know that's not what the one you're asking about, but I'll just state you could call the resultant or the overall vector B just whatever the x component is in the I hat direction and whatever the y component is in the j hat direction. So it would be whatever this number ends up being I hat plus whatever this number is, j hat. But the one that's a little bit trickier is the polar form, where you
Is
need,
that just the Pythagorean? Is that all that is?
yep, yep.
Okay, then never mind.
No, it's okay because the angle especially is tricky to get down. It's the one where I recommend ignoring the signs. You could even think of as absolute value because you can get some kind of funky negatives and stuff from your calculator that aren't always reflective of what's going on. If I did this with bx and by, but with their absolute values, I'd get 22 degrees as my angle. But since I knew that I used this formula because by was opposite this particular angle right here, that right from this perspective, I didn't know it yet, that it was 22. If I just decided, okay, this is the opposite side, this is the adjacent side because I'm working with this angle right here, I know that it's just telling me that angle is 22 degrees. If I want to correct and say relative to the positive x-axis, I could just call it negative 22 because it's below that axis. Or if it asks me for some weird reason to find it relative to the negative y-axis, well, that's not how this angle I've just found is measured, but the 68-degree angle is, and I could figure that out from just knowing that that is 22 degrees in absolute value. Does that make sense?
Yes, sir.
Okay. Maybe one last spot check. BX and or CX and CY. So this would be CX, this would be CY. Which one should I use sine for? Which one cosine?
CY is cosine
Why do you think so?
because it's touching the 44-degree angle.
Absolutely. And CX is sine because you got to go across. If I had, just as one last, by the way, if I draw my components the other way, I don't have an angle inside this right triangle that I've just drawn. So I got to find one. I might, for instance, realize that if this angle is 44 degrees, then the complementary angle to it is, oh, my Lord, math, 46 degrees. All right. If I used that 46-degree angle, which one do I use cosine for? Which one do I use sine for?
It's going to be inverted, so you're going to use sine for your CY, and you're going to use cos for your CX.
Yep, because when I go across for my 46-degree angle, that's where I see my vertical component, CY. If I'm adjacent to the 46-degree angle, then I see that I'm looking at CX, the way I've chosen to draw them. And this has become a mess, so maybe I'll clean up a little bit. Do y'all want me to go through the whole problem, or is the time better spent on a different one? Either's fine with me.
It sufficiently answered my questions as long as CY would be negative 88 cos of 44, and then CX would be 88 sine of 44 degrees, right?
Yes.
Okay.
Or
Then
wait,
I'm good.
but negative for CX as well, right?
Yes, because they're both the
Yes.
negative X direction, negative Y.
Yes. Okay. Yep, I agree. Okay. Does anyone else want me to continue going through it or jump to a different problem? I said I would do 35 and 36, but I don't want to go through it if everyone's like, yeah, of course, it makes sense.
Just to make sure,
Mhm.
so whenever the CY or CX is in the negative direction, we put a negative sign on the magnitude.
Yes.
Okay, thank you.
Yeah. Let me just to like if you're finding CX and or CY, yeah, you would put a plus or a minus depending on which way they're pointing. If we're talking C, the magnitude of the overall vector, that one doesn't ever have a negative because it is just the length of the vector. It's not saying anything about a direction it's pointing. That would be given by this other piece, the angle theta.
Thank you.
Mhm. Okay. Is there another problem that we want to look at? You all want to search around for one? I'll just draw this in and at least get it relabeled a little better while you're thinking about
Could
it.
could
Yeah.
you do one that of like the I guess where you figure out the height and then like of where the ball is launching? I don't know what those are called.
Okay, yeah, yeah. Projectile motion. We'll take a look in just a second. Let me just relabel these 44, and I'll just label the components real fast. So if I use this as bx and by, this is, bx is um, positive 11 kilometers cosine 22, by is negative 11 kilometers sine 22, and cx and cy I could do either way if I did it with these two. Oh, that's a little bit too long. Y, cx. This would be negative because it's to the left, 88 kilometers. I go across, so it's sine 44, and cy is negative 88 kilometers cosine 44. Okay, so a projectile motion problem, sure. Apologies about whatever happened with this first one, but it's one that I believe is in the examples. It's the watermelon seed one, maybe. Um, we can come back to one where something's being launched horizontally. I'll start with at an angle. How long? How far? Were you asking specifically about like the maximum height something reaches?
No, just like the whole problem.
Okay. Let's do these cannonball ones because it has something at an angle, and then I'll come back to some of these where it's horizontal. I could have stood to put a few more, but um, all right. Cannonball aimed 30 degrees above the horizontal. So I would start drawing a little cartoon even before I try and start labeling things. Uh, a cannonball, and it's launched 30 degrees above the horizontal. So I might say this angle is 30 degrees. Sometimes that can trip you up because a lot of the times this assumes that the cannonball or whatever leaves the ground, and it does state that here from ground level. So really, if I were being correct, it's more like the ball was launched like that. That's just to make the problem a little bit easier to work with because then your initial height is 0. So better to look at it as that being 30 degrees. Um, and an initial speed of 125 meters per second, and that will be the velocity. The directional bit of that is that it's tangent to this arc that the cannonball ends up traveling through. All right, how long does it take to hit the ground? So that is a thing that's determined by the ground, meaning a vertical thing. If there were a wall involved, the horizontal might become an issue as well. But if we're just worried about it leaving the ground, coming back, that's only determined by the vertical part of the cannonball's motion. So it's good, and really in general, it's good to go ahead and find my vertical and horizontal components of this initial velocity. I think that's a good first step in general if it's something you can find. And we find it just the same way. Should I use cosine or sine for my x component?
Cosine.
Cosine, because that side is touching the 30-degree angle. And it'll be 125 cosine of 30, and it would be positive because I've drawn this so that the ball is going to the right, and it'd be 0y. I will use sine. The way I've drawn the components doesn't necessarily make that clear. Um, I could have drawn it like that instead, and it's a little bit easier to see that way. Also positive because it's upward, sine of 30 degrees. So, in principle, I'm lazy, so I don't like to actually calculate anything till the end. But in principle, I know at the very least my initial vertical velocity. I want to know time. It's how long in that sense. I know my vertical acceleration, and I need one more thing to get my four things, three knowns, one unknown. So I gotta think usually more physically than math-wise to figure that out in these types of problems. What are my options here?
You know
Initial
your
velocity.
I think so someone go first, someone go second. I think I heard Gabriel and I heard, was it Obi or was it someone else?
I was just gonna say initial velocity.
Yeah, so that's I do know that. I do know the y acceleration. I don't know time and I want to know it, but I need a fourth thing in addition to those three to solve
I
this
was just
problem.
I was just gonna say we know the horizontal acceleration, right? It's zero.
We do. That is true. We do know that. And that means we also know the final horizontal velocity because it's going to be the same as the initial. The difficulty is that usually doesn't help us find the time unless it just tells us that something was traveling a certain horizontal distance, because our equation that would relate the acceleration to the velocities and time would be this one. And we'd look at that and say, oh, lovely, I can solve that for time. But then this thing is zero, and you end up with a divide by zero issue. And the reason is because this equation is true no matter what the time is, because the final and initial horizontal velocities are always the same no matter what you're calling your final position. It's not special to the landing point of the cannonball. So usually horizontal doesn't help us too much. We need a fourth vertical related thing. Well, we only have two other kinematic variables that could be an option, right? So vertical displacement, the delta y or just y, if you choose your initial height as zero, and then the final vertical velocity. Those are the other two kinematic variables in the vertical direction. So do I know something about either of those? That would be as the ball hits the ground.
Well, we know that the change in y is zero because it's gonna launch from a spot and it's gonna hit the ground.
Yeah. And now you have four things, three knowns, one unknown. And so this is a closed problem. So in this case, it would be the one that relates those four is this one right here. And there are other options. We'll get to that in a second. So let's see. I could use that other one. I'll get to that. So If I want to solve for time, this is a quadratic equation. You could use quadratic formula, or this is the one where you can kind of take the shortcut because you realize this is zero, and that can only be true if the right-hand side is zero, but you can factor time out of the right-hand side and get either this is zero or this is zero. And this first one's the one we want, we're interested in, because the second one is just when the ball was launched is the solution there. So we get v0y plus 1/2 ayt equals 0. And so t is, I need to bring v0y over to the other side, multiply both sides by 2, divide by ay. So it'll be that right there. And that's going to be whatever this number ends up being is what goes right here. And then over negative 9.8 meters per second squared. And our negatives cancel. That's a good thing because we hope our time is a positive number.
On
Yeah.
on the exam, are you looking for us for our transformation of those equations, or if we were to put like the quick answers on the cheat sheet, would you care?
Um, I'd say for one like this, where it's like there is a cut and dry formula, that's okay. I do prefer if you start from the kinematic equations, just because I know you're thinking it through rather than having a cookie cutter thing. But at the same time, I mean, I can't really blame you if it's there, it's there. Uh, I specifically think of this one, so the horizontal range of a projectile, because this is something you can derive from the kinematic equations, but also I see it applied to cases where it does not apply. And in particular, it doesn't apply if we're talking about how far to the right is the ball after some number of seconds that isn't it landing back on the ground. So like this, you cannot use that equation to calculate. You're going to get the wrong answer. It only works if the object starts and ends at the same exact height. But sorry, that's a tangent. Uh, I'm not going to count you off for the shortcut answers if they are still giving the correct answer overall.
Okay, thank you.
Um, okay, I want to just mention this other one because we went down the route of if we know why, but we also know something about Vy in this particular case, at least. What could we say about it?
Your Vy is the same as your initial velocity, right?
Up to one tiny difference,
Negative.
negative. So when the ball lands, because it has fallen back down just as much as it rose, it's regained any vertical velocity it lost by the time it got up here to the top. So Vy is negative V0y in the specific case that the ball is back at the height it was launched from. That's not true always like it is for the Vx and V0x stuff. So we could go that route and use, for instance, this equation. And that we could either put the number in and just say it's negative whatever this number up here is again, or I could write it as negative V0y equals this. If I solve that for time, I actually get the exact same formula as before, negative 2v0y over ay. So same as over here, just slightly different path to it. Or I could have used vy squared equals v0y squared plus 2ay delta y if I realized both things right here. But that's probably the least obvious path. Okay. What else? Can be concept questions. It can be really whatever. I'm just here until there are no more questions.
I actually had a quick question about this problem itself.
Yeah.
And others similar to it. So here you changed all your variables to apply only in the y direction, and I'm guessing, or I'm assuming that's because we were looking for the height.
Hmm.
And so if we're looking for like anything in the horizontal direction, will we change all of that for x's?
Yeah, yeah. So let me do both of these next two, and I think you'll see on that bit. But yes, that is more or less the idea is if I'm looking for something that depends on the vertical part of the ball's motion, I look at the Y stuff. If I'm looking for something that depends on horizontal, I look at the X stuff. In either case, if I don't think I have enough, then I start to look at what's going on in the other direction because sometimes that gives me something else to work with. So, for instance, how far away from the cannon will the cannonball hit the ground? In this case, we could use this formula, but I don't want to. I want to just go full on kinematic equations as usual because I'm going to pretend I forgot that that formula exists. Um, but again, if you use it, I don't mind. I'm going to say I want to know how far it goes to the right. That would be its horizontal displacement. And so I need to um, look at some horizontal related stuff to figure that out. I want to know horizontal, and I'm in kind of a nice way limited in the horizontal direction. I've really only got that the horizontal velocity doesn't change because horizontal acceleration is zero. And I've got that horizontal distance is that right there. So horizontal velocity times time. So how would I solve this one? These are really my only three options I have to work with.
You have your initial velocity, they give it to you,
Hmm.
and you have your time because you found it. So
Yeah.
just plug them in.
Yeah, but let me propose. Say this problem were given first. Would you think of doing the vertical stuff first? So if it asked you how far it went to the right, would you think about that to find that time, you need to think about the vertical motion as well? So
Honestly, I would probably go with just the V naught X or whatever, the projectile motion equation, because it's simpler.
tell me a little bit more about that, about what you mean there.
I don't have them in front of me, but if I remember correctly, there's a was it something cosine of theta for a projectile motion that's much simpler than going about the whole y um, axis.
Well, I mean, are you talking about this one that's over here on the left, this R equals stuff?
No, sir.
Okay. So I think maybe what you're talking about then is this.
Yes, that would be it.
That is this equation right here. It's the same thing. This is the horizontal component of velocity, right? It is V0x. So more what I'm asking is, say that we didn't do problem 43 first. Instead, we tried to do problem 44 first. That would mean we hadn't solved for this time yet because it was asking about it for some vertical motion related stuff. Then I would write this down and say, okay, so if I could just find all this, I'd be good. But then I'd look at the time and I'd realize I don't have that, but I also don't have this because it's what I want to find ultimately. So I don't have enough stuff to solve this directly. this is what I mean about sometimes you don't have enough things in one direction to solve the problem outright, and you have to dip into the other direction and see what's going on that way to get you something like the time. And that dipping into would mean you do the stuff we did for problem 43. Does that make sense?
Yes, sir.
Okay. Um, so how far away will it hit? It would be whatever this number ends up being, because that's V0x. It's V0 times cosine of theta, and then multiplied by whatever time we get from this equation. So I think the hardest part about these really is just kind of those physical observations that aren't always immediate, and you have to think through what it is that would help you find what you're looking for. All right, let's look at 45. What is the speed just before it hits the ground? So it does help to remember speed is magnitude of velocity. So this would be, you find the x and y components of the final velocity, and then you can find speed from that. So we've kind of already answered this and some others. How could we find our x and y velocities when the cannonball is just about to hit the ground? Okay. Um, what can we say about the horizontal velocity? What's special about it?
It doesn't change.
Doesn't change. So as long as we know what it was initially, which we do, it's 125 cosine of 30 degrees. We know what it is at the end, at impact. So that one's always easy. What about the vertical velocity? This is really the one where there's an easy way and a hard way.
Well, you mentioned to us earlier that it had to be that Vy equals negative V naught Y.
Yep. So that's the easy way. That's just seeing the symmetry of the problem. The hard, maybe not really hard way, but just harder, you just pick out a kinematic equation that has Vy in it and has otherwise things that you already know. So you could, for instance, do this one right here, right? You could write it with the Y naught, but we've just been assuming that's zero anyway. Um, and then you just solve this. So it would be, really, there's two roots. But since y is zero, this whole term goes away. Y is again zero because the ball left and hit the ground. So its vertical displacement is zero. And so really it's just about, you got to choose a root here. You choose negative because it's going downward. So Vy is negative V0y again. Or Vy is V0y plus AYT. If you do that one, it's kind of more direct calculation. It's just if you take V0y, which was 125 sine 30, and you add AY, which is negative 9.8, and then that time that we would have found from 43 and put that right here, you would again get Vy and find out that it was negative 125 sine of 30 degrees. So multiple ways about that, but once you get that, then you just go back up to here and you find your speed from those two components. And if y'all want me to calculate these out and like do the numbers as well, I can do that. I don't know if that helps any or not. Okay. Let's see. I've heard from a couple folks. I've not heard from a couple others. So anyone who hasn't asked any questions, do you have any? Because, now is the time to ask quote unquote dumb questions. It's more dumb to not ask the question right before the exam. Just clear it up. Make sure it makes sense.
Yeah, I have a question.
Yeah.
So, I think it's question number 15
Mhm.
on the practice exam. The acceleration of an object from rest shown in the graph, other than at t equals zero, when is the velocity of the object equal to zero?
Okay.
So I have no, you
Yeah,
can
go
keep
ahead. I'm
going.
sorry. No, you go ahead.
So what does it mean by other than t equals zero? Is it like finding the time throughout the graph?
Yeah, it's asking, so this is sort of a underhanded way of telling you that the velocity at 0 seconds is 0 meters per second, because what this problem actually is a numerical integration problem. It's the ones that look like this. So we need to specify initial velocity in order to find final velocity. That's the reason it tells you that bit of t equals zero. And this other than piece is asking you, when else? When else do you see that v equals 0 meters per second?
Yeah.
Do you want me to go through like how I would figure out from there?
Yes, sir.
Sure. Okay. So I would look at this. We kind of more think of it as integral of blah, blah, blah is really area under the acceleration time curve. And that's what we're given in this graph. So one way I could think about finding out when the velocity is zero again is that means my initial and final velocity are both zero. The left-hand side of this is zero. That means the right-hand side has to be zero. And so it's really asking when, after how much time, is the area under this curve equal to zero? Which sounds a little bit weird, but you got to remember that when things go below the axis, you count that as a negative area. Do you kind of see from here where we might go?
You might go to like four, time equals four, or
Yeah, yeah. So somewhere over here is our guess because let's kind of think about what happens as time goes on. Um, right here, this is where we're told we know that we are at rest for just a little bit. This tells us, okay, tack on to that, add some velocity to that. So we're speeding up right now. Okay, now we're at a constant acceleration that's still tacking on to the velocity. That's still adding these little bits of area, these rectangles, onto your overall velocity. It's only after this point right here, about 3.5 seconds, that we start taking off, taking away from that velocity. And so it's got to happen somewhere over in this region where we're taking back away from the velocity that we can ever get back to zero velocity. Does that make sense?
yeah, that makes sense.
Okay. Yeah, you go ahead. You tell me what you're thinking.
So like when the acceleration decreases, it'll be like we're at the end where four and five, so it'll be either four or five that's like the duration of equal to zero because it's
Mhm.
during it's on the negative side.
Yeah. And so we're kind of narrowed down to one of these three. Either it does reach zero because this negative area really does take away all of that positive we gained, or it just isn't quite enough, meaning this is what happens. We don't ever get back to zero again. So how we go from here is we figure out how much area we accrued how much velocity we built up, and then see if there is an area in here that takes all of that away. So I think from here, I'll just go ahead and do that. So let me figure out what area I have here first. Help me out with that bit. How much area do I have in this part of the graph?
3. Yeah, area.
Let's see. So what's the area of this triangle going to contribute? And anyone can chime in on this. This is for everyone.
Wouldn't it be 2.5?
Yep. It's 1/2 base times height. Our units would be 2.5 meters per second. That's how much velocity has tacked on to our initial. In other words, at 1 second, we are going 2.5 meters per second. That's how much our velocity has changed. All right. Now I see this rectangle. How much more area does that add?
10.
Okay, yep, 2 seconds, 5 meters per second squared. So it's going to tack on another 10 meters per second, meaning at 3 seconds, I'm going 12.5 meters per second. All right, now this little triangle.
2.5.
Let's see.
What's
So this,
half?
yeah, it's a 1/2 second, so 1.25, right? Does that sound kosher?
Yes.
Okay, yeah, 1/2 base times height. The base is a 1/2 second. And so 5 times a half is 2.5, and then you take a half of that, 1.25. And so at this point, we've accrued 13.75 meters per second of velocity. That's how fast we're going at this point, and that means that's how much we got to pull off now with this negative area. So we have to check if that can even be done. So I would then see, all right, how much area does this take off, take away from that?
Not enough.
Not enough. Yeah, it's actually going to take off 1.25 again. So I think that is minus 1.25. In other words, I'm now back to 12.5 meters per second. And then this area is, let's see, 1, -5, so negative 2.5. And that's only going to pull off another 2.5. I am now, by the time I reach this point, going 10 meters per second again. I dropped from 12.5 by 2.5 meters per second. My final velocity is 10. I was not able to undo all of that area I added. And you can kind of see that visually without the calculations, but that would mean the answer is E.
Oh, okay, I get it.
Yeah. Okay. Other questions?
I actually have a question about 44. We already did,
Yeah.
and I just wanted to do like kind of like a check for understanding.
Hmm.
So if we were given 44 first without time,
Yep.
um, we could use the last kinematic equation to solve it, correct?
So, meaning this one right here?
No, I was meaning final velocity squared equals initial velocity squared plus 2 times acceleration
multiplied by the displacement of x.
Okay. Um, so let's look at that one actually. Because I do think first glance, it is a good choice. Do you see maybe what's wrong with it? Let's write it like this.
Oh, it's what you were talking about earlier, wasn't it? It's the divide by zero error.
Yeah. Yeah, and it's still okay because Vx and V0x are equal to each other as well. So it's really an indeterminate form, 0/0. Um, but it's because this just is another version of the equation Vx equals V0x. It's all this stuff goes away. So it's not super helpful, and that's why we have less kinematic equations in the x direction than we do in the y direction for projectiles.
Okay, I see that. I was wondering why we didn't use that equation. I see
Yeah,
why now,
yeah,
definitely.
that's a really good question. That's also why this one's gone. Well, actually, this one's still okay. It's just it reduces to, well, V0x and Vx are the same number. So you have two V0x. The twos cancel. So this is really just this equation again. In other words, I guess the math term for this would be that the equations degenerate into less equations.
Okay, so we're
Yep.
forced to find T first then.
Yep. Yep. Yeah, that's a really good one because I think I could really see someone doing that and then being like, uh-oh, yeah, so you do need to find time and that dips into the vertical motion.
Okay, yeah, thank you for that clarification.
Mhm. Okay, other questions.
I just have one general question. Is
Uh-huh.
the whole test is going to be multiple choices?
Only the conceptual questions will be multiple choice. I'll tell you why. I used to do multiple choice for the calculation as well, and I think it didn't help because you would see an answer that you wanted it to be and make your work fit that rather than doing work and seeing what answer you got. And it usually did not work to people's benefits in past courses. So only concept stuff is multiple choice.
Okay.
Yep.
I prefer the multiple choice for myself, but like me myself, but that's
I do
fine.
get it, but I really have seen. There's especially when we get to force stuff, there's ones that, there's always a trick answer that's the one that people always think is the case. For instance, saying that normal force is equal to weight is something we'll say is not always true, but it is a very common thought. And so that goes as one of the choices, and it always gets picked, and someone makes their math try and fit it, and it just no partial credit can be, or very less partial credit can be given in that case than if they just gave it their best shot.
That's right.
Yeah.
Totally agree.
And I am a big proponent of partial credit. It's not all or none. So I just want to see the attempt. And if you have no idea on a problem, I still want you to write something so I can give you something.
Okay.
Okay, other questions?
So since this is this the midterm from last semester?
This is just a bunch of practice questions, but that is also posted. So that's this over here. So yeah, we can take a quick look through this so we can kind of see what it looks like. So position time graph stuff. This would be the numerical integration because you're trying to figure out how far it went, but you're given velocity, so you have to integrate to get position. What are the velocity and acceleration? You need to take a derivative. Even gave you the power rule. Um, Speeding up, slowing down. When does the car stop? A little bit of free fall stuff. Um, this is vector addition, projectile motion. This stuff did not, oh, we didn't cover this, so these questions are not relevant right now. We'll get to this stuff a little bit later.
How many questions will most likely be on the test, Professor?
I think a number like this is usually a safe bet. How I try and do it is shoot for about a third being conceptual. So if we count these off, I see one, two, uh, three, four. Okay, I got 4 out of 15, not quite a third conceptual. And then it's just whatever needs to be done to get coverage while also not feeling like I'm giving you stuff that can't be completed in time. So when I write the exam, I do it myself. Now, granted, I wrote it already, so I should know roughly how the problems go. So I try to account for that. But I just take my number that it takes me to do, multiply it by 4. If that still gives you enough time, like plenty of time after, then I usually say, okay, that's pretty good. So I don't have a definite number, but I think, 12 to 15 is not unexpected or something you could expect, I guess I could say.
Okay.
But also bear in mind when I say that it's like it helps to do this problem to do this problem. And so they're kind of really breaking one problem down into smaller parts. Hey,
Your mom.
I'm sorry, what was that? Okay. Um, all right. I'm happy to keep going. I'm happy to call it a day. It's been a long day, I know, especially with the end of the day and whatever died in Manning Hall did not make for a good day. Apparently something did actually die in the basement, and I don't know what it was, but yeah, at least your office isn't right by it.
Do you know what died?
I heard potentially a possum or something, but it was down in the basement below us. I didn't really question beyond that. I just tried to power through.
My
Thank
roommate was
God
talking to me about it, and he was saying like it smelled like rotten eggs in there.
Yeah,
it's awful.
it was really bad. And on with how hot they keep it in that building already, it's not a good environment for that. Uh, so that's I don't know, that's U of M, I guess. Um, Other non-dead animal related questions.
Are we allowed to do one from this sheet right here? Or are these answers already posted or something?
Yeah, the whole key for this exam is posted, so it's what I graded based off. So you can even see how I assigned points for each question in that key.
Okay, could we look at number 1 or 2?
Yeah. Um, so do you want through the key or like just my me looking at it right now going through it?
Yeah, you just looking at it.
Okay. All right. So graph represents the straight line motion of a car. What is its acceleration at 1 second? So if this were my first time seeing this, I'd look at that and say, okay, it wants me to know the acceleration right there. My first thought might be, but I don't know necessarily that the value of the velocity is 6 there when it's 1 second. I'm just kind of eyeballing and guessing that's true. So I wouldn't go with that, but I would realize the slope right here, which is what the acceleration is on a velocity time graph, is the slope, is the same as the slope of this entire line. And so I would look at the endpoints of that line to find my slope because those are numbers that are guaranteed. Now it would end up giving me the same acceleration, but I would do, okay, this is final minus initial velocity. Oh, and one more thing, I slipped under the rug here. This is the formula for average acceleration, but I would remember that average and instantaneous are the same, specifically when the graph is a straight line. Because of this thing we just said of the slope at a single point is the same as the slope between 2 points. So I would do 12 meters per second. That's the final. Minus initial is 0 over the time span of 2 seconds minus 0 seconds. So I kind of worked around this 1 second time it's asking me about, and I would get positive 6 meters per second per second. Does that all track?
Yeah, that makes sense. That makes sense.
Okay. All right. So number 2, how far does it travel between 2 and 5 seconds? So I would look at that and say, all right, how far is either distance or displacement? Um, we always stick with displacement anyway, so I would lean towards that one. But if I wasn't sure, it turns out it doesn't really matter either way. Since this graph is always positive, I'm only ever adding to my velocity. And so, or I should say my position. And so I'm not ever turning around. And that's when distance and displacement begin to disagree in 1D is if you start turning around, backtracking, all that stuff. So this is just asking me, all right, what's my change in position? Between 2 and 5 seconds would mean I need to integrate between 2 and 5 seconds. And so that's going to be area under my velocity time graph from t equals 2 seconds to 5 seconds. Or the formal way of writing that would be 2 seconds, 5 seconds, v of t with respect to time. But it's really just what's the area of that rectangle. Its base is 3 seconds. Its height is 12 meters per second. So this would be positive 36 meters. That's how far I've moved in that time interval. And that's really just a fancy way of writing x minus x naught equals v naught t, specifically because the velocity is constant during that time interval. Also okay, or anything you want me to
Yeah,
recap?
no,
Okay.
yeah, that's good. I don't know why that one stumped me because now when you worked it out, it looks completely fine.
That's just how it goes. I mean, if someone says anything confidently, it's like, yeah, sure, I buy it. So if anything does feel like I skipped a step or like swept it under the rug or any, let me know.
No, yeah, I think it looks fine because at first, to be honest, I didn't know how to integrate it, but then when you started talking about area under the graph, that made sense. And then I guess you would just look at the graph visually, see that from 2 to 5, the velocity is constant, like you said. So
Mhm.
you would just integrate 12, which is just 12t, and then plug in your time, right?
Yeah, yeah, that's a totally equivalent way of looking at it.
Okay, yeah, that makes sense.
Okay, yeah. So yeah, if the because your v of t over that span would be 12 from 2 seconds to 5 seconds. That's 12t evaluated between 2 and 5. That's 12 times 5 minus 2. Yeah. Okay. Any other questions? Oh, and this, why did I even leave those on? I swear I took those off. Oh, it's 'cause, okay, this is the exam. I did take those off. So these down here don't show up on yours because For one, I decided not to cover relative velocity, and this stuff is going to come a little bit later. All right. Concept questions, anything from quizzes, from anything? How about I'm going to do 3 and 4 real fast. If there's no questions after that, we'll call it a day. Just because I want you to see how I approach this one, speeding up, slowing down, or not changing speed. Because when you have the derivative stuff, the math part of it, it's not as clear cut, I think, as when you have the pictures of it. So what is the velocity at 2 seconds? That's pretty straightforward, just dx dt. So ddt of 27t minus 4t cubed. That's going to be 27 minus 12t squared. And we want it at 2 seconds. So that's 27 minus 12 times 2 seconds squared. That's going to be 27 minus 48, which is negative 21, I think. The acceleration, dv dt, so derivative of 27 minus 12t squared is going to be negative 24t. And so at 2 seconds, that would be negative 24 times 2 seconds, or negative 48 meters per second per second. So is the car speeding up, slowing down, or not changing speeds at 2 seconds? What do y'all think?
It looks like it's slowing down.
What makes you say so?
At 2 seconds, the acceleration is negative 48 meters per second squared. So every second, it's decreasing its velocity by 48.
But which way is it going?
Wouldn't you have to calculate the distance according to that time?
You don't have to, no. How can we tell which way this car, or what? Yeah, it's a car. Which way it's going right now?
If you, I'm just telling you the way I know it. 2 times 2 is 4. 4 times 2 is 8. 8 times the 4 is 32, and you're subtracting that. So, I mean, is it a negative displacement?
It would be. So that is an option. I don't mean to say that's not an option. But there's a way from the work I've done here already.
You look at your velocity, right?
Yeah. So it's going in the negative direction, but my acceleration is in the negative direction.
Oh, okay,
They
I
agree.
see.
Yeah. So I'm just going to the west instead of east. I'm still speeding up though. So
Oh,
it's a little
okay.
bit harder to see from these. It's the only thing that matters is how the signs of your velocity and acceleration compare to each other, not their actual values.
Right. Yeah, that makes sense.
Yep. Okay. If we wanted to find at what position the car momentarily stops, how would we do that?
Solve for zero with your equation.
Which one? I got at least three: position, velocity, and acceleration.
What was your original question?
Just number 5. At what position does the car stop?
Velocity has to be equal to 0 because position could be equal to 0 and it still have
Still,
start with a velocity.
yeah, it could still be moving. Exactly right. So I need to figure out when the velocity, which is this right here, is equal to 0, and that's going to be when t is whatever square root of 27 over 12 is. And it would be plus or minus, but you're starting from time t equals 0, so we would throw out the negative root and just worry about the positive. That's going to be the time where we stop. We throw that back into our position equation, minus 4t cubed. So that would go in for t in both of these, and that'll give you the actual position where you stopped. Okay. Um, are there any other questions?
No, sir.
Okay. If there are, and they just pop up later, just email me. I will get to it as soon as I can. There will be at least office hours tomorrow and Monday if there are questions from 1 to 3 p.m. And otherwise, I will see y'all on Tuesday.
Yes,
All
sir.
right, thank you.
For doing
All
that.
right,
Alrighty.
thank you, sir.
Uh-huh.